Welcome to Get Educare. In this video, the EMF equation of transformer will be derived. Let us consider a two-winding transformer. The primary winding has N1 number of turns and the secondary winding has N2 number of turns. An AC voltage is applied to the primary of the transformer, and consider the transformer is in no load condition. That means no load is connected in the secondary of the transformer. Now if I apply AC voltage V equal to Vm sine of omega t, then a magnetizing current I mu equal to Im sine of omega t will be drawn from the supply, which is alternating in nature. Due to this alternating nature of current, a flux phi will be produced in the primary winding which link both primary and secondary. As a result, according to Faraday's law of electromagnetic induction, an EMF will be induced in the primary of the transformer E1. Similarly, since the phi links with secondary also, an EMF E2 will be produced into the secondary winding also. Now, as we know, the flux phi equal to mmf by reluctance. Now, mmf is the ampere turns. Ampere is the magnetizing current, I mu. Primary turns is the suppose N1 by reluctance. Now, what is reluctance? Reluctance is the opposition of magnetic core for passing of flux. Now, reluctance formula is the reluctance equal to L mu 0 mu r into A. The L is the length of the magnetic path, mu 0 is the absolute permeability, and value of mu 0 equal to 4 pi into 10 to the power minus 7 Henry per meter, and mu r is the relative permeability. It depends upon the magnetic material. Higher the magnetic property of the material, value of mu r is very high. A is the cross section area of the magnetic path. Now phi, from here I can write down phi equal to, since I mu magnetizing current is the alternating nature, Im sin omega t. I can write down Im sin of omega t into N1 by reluctance. That is equal to Im N1 by reluctance into sin of omega t. This term Im N1 by reluctance, that can be represented at phi m. Therefore, phi of t equal to phi m sin of omega t. Now, according to Faraday's law of electromagnetic induction, the induced EMF in the primary winding E1 will be proportional to d phi dt, rate of change of flux. Therefore, E1 equal to minus of N1 d phi dt. The minus sign represents the opposition of induced EMF of the required flux. E1, we can write down E1 equal to minus of N1 d by dt, and what is the phi equal to phi m sin omega t. I put down here phi m sin of omega t. If I do the derivative, then E1 equal to minus of N1 phi m omega and cos of omega t. That is equal to E1 equal to N1 phi m omega. The cos of omega t, I can write down sine of omega t minus of 90 degree. It can be represented at E1 to t terms of t. This term can be represented at maximum value E1 max sine of omega t minus of 90 degree. E1, the maximum value of induced EMF, E1 max will be the N1 phi m into omega. N1 phi m into omega. Since the induced voltage is alternating and sinusoidal in nature, the RMS value of induced EMF, that means E1, will be the maximum value divided by root over of 2, E1 max divided by root over of 2. From here we can write down E1 max equal to N1 phi m into omega equal to N1 phi n into 2 pi f. Since omega equal to 2 pi into f. Therefore, the RMS value of the induced EMF is given by, if we put the value of E1 max here, to N1 phi m into 2 pi f divided by root over of 2. If we do the simplification, then we get E1 equal to 4.44 phi m f into N1. This is the equation of induced EMF of primary of transformer. You have to remember this formula, equation number 1. Now, if we take it is a ideal transformer, that means leakage flux is 0. The flux which is produced into the primary winding link with the secondary winding, then we can say the induced EMF in the secondary winding E2 will be proportional to d phi dt. Again, if we do the same process of derivation of induced EMF, then the induced EMF in the secondary winding will be given by E2 equal to 4.44 phi mf into N2. This is the induced EMF in the secondary of the transformer. Question number 2. Now, if I divide the equation number 1 with the help of equation number 2, then we get E1 by E2 equal to 4.44 cancel out, phi m cancel out, f will be cancel out, N1 by N2. N1 divided by N2. We have to remember this formula. This is the E1 by E2 is the voltage ratio equal to the N1 by N2 is the turns ratio. Again, we can write down E1 by N1 equal to E2 here, E2 comes up by N2. This is, we can say, this is the EMF per turn of primary equal to EMF per turn of secondary. That means EMF per turn of primary equal to EMF per turn of secondary. Now we will derive the phasor diagram of transformer. The phasor diagram will not the full phasor diagram of transformer. It is the phasor diagram of ideal transformer at no load condition. Slowly we derive the full phasor diagram. Okay. Now the flux phi equal to phi m sin omega t, which is common in both primary and secondary winding. Therefore, phi is taken as a reference. First we draw the phi. Now the magnetizing current I mu equal to I m sin omega t in the same phase. Sin omega t is sin omega t. That means the magnetizing current will be in phase of phi. From here we see the induced EMF is the sine of omega t minus of 90 degree. That means induced EMF E1 lags phi by 90 degree. The E1 will lag phi by 90 degree. Again, E1 by E2 equal to N1 by N2. Depending upon the value of number of turns, E2 may be greater than or less than E1. Suppose here N2 greater than N1. Suppose here N2 greater than N1. Therefore, E2 will be greater than E1. According to Lenz's law, the effect opposes the causes. An effect is the induced EMF and cause is the supply voltage. Therefore, E1 will be minus of V. It will be the same, both E1 will be the same but in opposite direction. This is the supply voltage V. As we know, the EMF equation of transformer E equal to 4.44 phi m F into N, number of turns. Now, since phi m flux equal to Bm flux density into area, cross section area. Therefore, we can write down E equal to 4.44 Bm A F into N. Now, if we increase the supply frequency F, then for a constant voltage, if we have to maintain the constant voltage, then the area, cross section area will be less. The one point is clear. If for same kVA and current rating, for same kVA and current rating, if we increase the frequency, then the cross section area, that means size of the transformer, will be less. Now for this question, which of the following transformer is the smallest in size? This is 100 kVA, 100 kVA, 100 kVA, 100 kVA, same rating, kVA rating of the transformer. The frequency is 25 Hz, 50 Hz, 75 Hz and 100 Hz. The highest the frequency, higher the frequency, smallest the size. Which is the smallest size? This is 100 Hz frequency of transformer is smallest in size. In normal application, generally frequency is maintained at 50 Hz. But in aircraft industry, the frequency is 400 Hz. Why? The reason is that, as we discussed earlier, that if we increase the frequency for the same kVA and current rating, the cross section area of transformer or any electrical machines decreases. Therefore, size also decreases. In aircraft industry, the size or weight is our main concern. Therefore, to reduce size and weight, the frequency is increased and is maintained at 400 Hz. But in household application, the normal application, the weight is not so much important. So we maintain frequency at 50 Hz. Now the question arises, why it is 400 Hz? Why it is not 1000 Hz, 4 kHz like this? If we increase the frequency, the weight will be reduced and it is beneficial for us. Now, as we know, xc equal to 1 by 2 pi f into c and xl equal to 2 pi f into L. As we increase the frequency, then xc will be reduced, and if we increase the frequency, xl will also increased. Then what will happen? If we increase the frequency very high, then there will be interturn capacitance between the coil of the transformer winding. Due to this interturn capacitance, suppose this is the I mu equal to 5 ampere, magnetizing current 5 ampere. Now, since xc is very less, than compared to xl, then maximum current, the 4.9 ampere, will passes through the capacitance. Only 0.1 ampere current will passes through the coil, and transformer will not operate properly. Therefore, will maintain optimum value of frequency like 400 Hz. Again, the Emf equation of transformer equal to 4.44 Bm AF into N. For the same rating of the transformer, that means E equal to constant, if I increase the flux density Bm, then the cross section area A of the transformer will be decreased, size of the transformer will also decrease. By designing the transformer with superior magnetic material, that means CRGO process, the Bm maximum flux density increases, area of the cross section decreases, that means size of the transformer also decreases. 2 point, number 1, by increasing the supply frequency, A cross section area decreases, size decreases. Number 2, by increasing the flux density by using the superior magnetic material, the size also decreases. Thank you for watching my video. Please subscribe my channel and share to all of your friends so that you don't miss any notifications. Thank you once again.